Hi, I'm Teacher Thomas. Welcome to A-Level Maths. This is the specimen paper for 9231 Further Pure Mathematics 1 for the 2020 exam series, question 7, D and E. Given curve C, requirement D, sketch C, stating the coordinates of any intersections of C with the coordinate axes and the asymptotes. Requirement E, sketch the curve with equation y equals the absolute value of the original function, and find the set of values of x for which that absolute value is less than 2. I'll start by drawing in the asymptotes. We previously identified an asymptote, vertical asymptote at x equals 1. A horizontal asymptote at y equals 2. We haven't yet calculated our roots. We haven't determined where y is 0. I'm going to take the numerator, 2x squared minus 3x minus 2, set the numerator equal to 0. Those x values will be the roots. X equals negative 1/2 and 2. So our curve is going to cross the x-axis at negative 1/2 and at 2. I'll write in these are x intercepts. We also want to find the y-intercept. We set x equal to 0 in the original function, and the result will be y equals, the first term will be 0, minus the second term is 0, minus 2. In the denominator, first and second terms are 0, plus 1. The y-intercept is negative 2. I'll mark negative 2 on the y-intercept. Regarding the asymptotes, we'll never have an intersection with the vertical asymptote, but we might with the horizontal asymptote. So we'll analyze at y equals 2. If we input 2 into the original function, we have an x value of 4. One point on the curve is 4, 2. I'll mark 4 on the x-axis, and then on the horizontal asymptote, the point 4, 2. Before we complete the graph, I want to extend the horizontal asymptote to the right. I'm also going to extend the x-axis a bit to the right. There's one point I want to identify on the curve that isn't a requirement, but it is an interesting point to relate to other work we've done previously. I'll begin on the left, the points negative 1, 0, and 0, negative 2. Given the intercepts, I calculated only one intersection with the horizontal asymptote, so I won't be crossing the horizontal asymptote again. I never cross the vertical asymptote, so the left part of the curve looks like that. On the right side, we're going through the point 2, 0. We're crossing the horizontal asymptote at 4, 2. What's going to happen after that? Well, let's go back and reference the maximum that we calculated. At x equals 7, we found a maximum value of y equals 25 over 12. So at the point 25 over 12, we begin to decrease in y value. So I'll go up through 2, 0, 4, 2, 7, 25 over 12. At this point, I'm decreasing. I didn't calculate any further cross through the horizontal asymptote. I'll be getting closer and closer to, but never touching y equals 2 at that point. This completes the requirements for part D. Going on to part E, you would, on the paper in a separate section, sketch a new graph. What I'm going to do is, in red, I'm going to sketch E. E is the absolute value of our function. So any negative y values we reflect through the x-axis to positives. The E graph will keep where we have positive y values now. Those parts of the graph will continue to be part of the absolute value graph. And then the negative y values will reflect up through the x-axis, an intersection with the y-axis at y equals 2. At x equals 2, we reflect through the x-axis, approaching but not touching x equals 1. The second part of requirement E, find the set of values of x for which the absolute value of the function is less than 2. We'll do this less than 2 analysis in blue. If I look at the red graph and look for everything that is less than a y value of 2, working from the left, we go as far as y equals 2. So we'll quantify that blue component on the left side of the coordinate plane. And on the right side, we have y values that are less than 2 from some unknown as of yet x value up to x equals 4. And I'll mark in blue with open circles to emphasize that we're not including the y equals 2 values. What we need to find is this point here that is somewhere between x equals 1 and x equals 2, where the absolute value function is y equals 2. If we think back to where that point would be in the regular function, y equals negative 2. So I'm going to solve putting negative 2 in as the value function. Negative 2 equals 2x squared minus 3x minus 2 over x squared minus 2x plus 1. When I cross multiply, simplify, and find my x values, I get the values x equals 0 and 7 over 4. Recall what we're looking for is we're looking for on the graph the point of intersection of the horizontal axis, that's the y equals 2 in absolute value, which we recognize as y equals negative 2 in the original function. That's why we use negative 2 for y. We're looking for an x value that's between 1 and 2. We can observe on the graph that the x value is between 1 and 2. That value in the two solutions we've arrived at is 7 over 4. I'll now mark on the graph 7 over 4. Finding the applicable x values doesn't require graphing, but it helps me visualize to identify what it is that I'm looking for. So now I can identify on the left, if I look starting at the y-axis, I see the blue values on the left. X is less than 0. All x values less than 0 result in y values less than 2. On the right, I can see starting at x equals, on the right I can see that from x equals 7 over 4 to x equals 4, excluding those two values, we have y values less than 2. So 7 over 4 is less than x is less than 4. I'll take these two x intervals and I'll use the intervals in my final answer. X is less than 0. 7 over 4 is less than x is less than 4. This completes the requirements for question 7, D, and E.